Right, so we were studying about biochemistry, remember? In our previous class, right? We looked at how the change in stereochemistry at a single position can completely change the chemical and physical properties of a given structure, right? The examples were of cellulose and starch. Then, for the most part of our previous lecture, we were talking about chirality. So chirality in molecule is handedness, as the right hand is not a superimposable mirror image of the left hand, although it may appear as a mirror image. So we have molecules like this as well. Those are called enantiomers. Okay? So, roughly speaking, achiral carbon is the one where we have some sort of symmetry. And those two elements of symmetry that we considered in our previous class was plane of symmetry as well as the center of symmetry. So if the molecule has, or any object, if it has one of these two elements of the symmetry, then the molecule cannot be chiral anymore. Right? So we also looked at it from examples, how plane of symmetry would look like, and how center of symmetry would look like in actual molecules. The most important concept for previous class was chiral carbon. So chiral carbon, aka the asymmetric carbon, is the carbon in a molecule which is attached to 4 different groups. Right? So when the molecule is attached to 4 different groups, I mean the carbon where we are talking about the chiral center here, so then the mirror image of that molecule is not superimposable on the original molecule. And this relationship is called enantiomers. So right here in this example, imagine that left hand side is the molecule and then right hand side is its isomer. Then these two isomers are called enantiomers because of the asymmetric carbon. Right, we looked at further examples that why this is the case, because when even 2 groups are same, then the mirror image can be superimposable on the original molecule. And that's why we lose chirality if even the 2 groups are same on any given carbon. Correct? So in this case, we can rotate the molecule and we'll get the original molecule just by simple rotation. Yeah, and this is because now the molecule has plane of symmetry to this angle, right? Then these were the types of isomers, stereoisomers that we were talking about. So your given compound may have stereoisomers. If it doesn't have chiral center, then the stereoisomers will be either cis trans or EZ isomerers, and they are called diastereomers, right? Diastereomers are simply the isomers which are not mirror images of each other. So cis trans, of course, will not be mirror image of each other. There will be different isomers in terms of stereochemistry. That's why they are good examples of diastereomers. But if we have a chiral center or asymmetric carbon, then based on different classification, we can have meso compound or diastereomers or enantiomers. Enantiomers will be the one where we have the mirror image relationships. Diastereomers will be the one where we have no mirror image relationships. And meso compounds will be the one where we'll have some sort of symmetry. Even though molecule has the chiral center in them, but the overall molecule would have a plane of symmetry or center of symmetry, which will make the overall molecule achiral or non-stereochemically active. Right? Then we looked at examples of enantiomers, I think. Right? And why this is important? Because so many reasons, our senses and so many other biological functions, they require the particular stereoisomer which is responsible to be attached to those receptors. So most of the biological system is like the receptors are made up of proteins, lipids, carbohydrates, and those are all chiral molecules. So when chiral molecule will come in the, in neighboring of a chiral environment, then we need the exact lock and key model, like lock and key model. So we need the exact enantiomer or exact diastereomer which will be responsible to be attached to that particular receptor. Otherwise, we may have loss of activity, or in some cases we can even have adverse effects, which we look in the examples of thalidomide. Remember that the case of Germany where a lot of birth defects were caused because the clinicians there recommended the wrong isomers. Yeah? Then we looked at a few definitions such as what is racemic mixture, and then how can we isolate the two stereoisomers from each other. So the racemic mixture is, generally speaking, 1:1 mixture of the two enantiomers. So if you have one as R, the other as S, you combine both of them in equal concentration, that mixture will be called racemic mixture. And if you want to separate the racemic mixture, the process is called resolution. You can use chromatography and so many other techniques to technically isolate any of the given stereoisomers. The final topic which we discussed in our last lecture was about the RSN configuration. So R and S configuration tells the orientation of these enantiomers that we are talking about. So one of them is called R based on certain factors as dictated by CIP conventions, and the other one would be called S, right? Then we looked at how we can decide on which one is R and which one is S. So for that we need to prioritize first. Based on CIP conventions, we go to next connecting atoms, and if the next connecting atom has a higher atomic number, then that whole group gets higher priority. Once we assign priority, we need to see where number 4 is. Number 4 must always be behind the plane for the rules to work. If it's not behind the plane, then we need to tweak our rules a little bit. Imagine that if in the given example like this, number 4 is behind the plane, then clockwise rotation will make the molecule R, and anti-clockwise will make it an S, right? But if number 4 is not present behind the plane, if it's present above the plane, then I told you the trick. Let's just stick with the trick and forget about the rotation. So the trick tells you that you can still do the rotation, but you will have to reverse your answer because number 4 is opposite of where it's supposed to be. That's why anti-clockwise will become R and clockwise will become S. Right? That was the case 2. And finally, the only hypothetical case could be where number 4 is present on the plane. So I told you the trick in this case that you can switch number 4 with the group which is already behind the plane and redraw your structure. So you will redraw the structure by switching these two, and then you do your rotation, and you will still have to reverse your answer because you have done a 90-degree flip, technically speaking, to the molecule, which is not allowed. You can rotate the whole molecule 180 degrees, then you will not have to switch your answer. But since this is a short-range trick, and we are only doing one switch, so in that case, we will still have to reverse our answer. Okay? We will do a lot of these practices in our tutorial session. So today we had one group. I am looking forward to that, and that will be my last class with you as well. I will get back to this point. Please remind me at the end of class that I'll have to make an announcement about next week's lectures, which happens to fall on public holiday. Right? Any questions from the previous discussion that we have been revising just now? Everything okay? Right? Right, so let's begin from slide 29. So all these things that we have been doing so far about the stereoisomers, they may sound like too hypothetical, that this role, that role, and you do this, you do that. How do we actually get to know that if a compound is optically active or stereochemically active in real world? So to do that, we use an instrument called polarimeter. So polarimeter converts the normal light into plane polarized light because that's its name. It's a polarimeter. You can put a prism or specific glasses which can convert the ordinary light which is revolving in multiple planes, and you can polarize that light into single plane. So those lights which you pass from the polarizer are called plane polarized light. Now all stereochemically active molecules, meaning enantiomers, diastereomers, and all these stereoisomers, they have the capability to rotate the axis of plane polarized light to some direction. Either they will rotate it to clockwise or anti-clockwise direction. And with that we can tell that if the molecule was actually, stereochemically active, or was an enantiomer or diastereomer or whatever. If the polarimeter reading is 0, meaning that the plane polarized light did not move anywhere, that could mean two things. Either our product, the sample that we are testing, is a racemic mixture, meaning that the left hand side and right hand side molecules are present in equal amount and we are cancelling each other. Or your molecule is simply not stereochemically active, right? So to do that we need plane polarized light, which is the job of polarizer. Yeah, so when you put a sample in the path of plane polarized light, then you will change its plane to either clockwise or anti-clockwise, and based on that we can say that the given stereochemically active molecule is dextrorotatory or levorotatory. Dextro would mean clockwise, levo would mean anti-clockwise. Or dextro would mean right hand side, levo would mean left hand side. Right, so clockwise would be dextrorotatory and anti-clockwise would be levorotatory. So now you are able to relate these things, right? This is a practical thing. This is not all hypothesis or theory that you have to just memorize rules to assign R or S, or just look at them in different ways to tell that if they are enantiomers or diastereomers of each other. This can be determined with the help of experiments. Yeah, that's my point here. And why this is important? So that we can use the right stereoisomer for its right application. And we saw in previous slides that how having a wrong isomer can make all the difference in losing activity or even causing adverse effects, right? But keep this in mind that R and S are IUPAC rules. This clockwise does not mean R, and this anti-clockwise does not mean S. R and S are still hypothetical rules which are given to name the isomer. But practically they could be dextrorotatory or levorotatory. So if you would have studied carbohydrates ever in your life, then you will remember D-glucose and L-glucose, right? Or L-amino acids and D-amino acids. So these L and D are coming from dextrorotatory and levorotatory. So those are practical terms. But R and S is an IUPAC term. It does not mean that this molecule will rotate the light to one direction or the other direction. R can be dextrorotatory or S can also be dextrorotatory. So D and L or dextro and levorotatory are practical terms. Yeah. Now this experiment also has some shortcomings because the extent of the light or the concentration of sample can also impact the rotation of plane polarized light. So we have, the chemists or scientists have standardized this calculation, and that is called specific rotation. So when we are talking about any given stereoisomer, its specific rotation will tell you that at a particular condition, at a particular concentration, at a particular temperature, how much plane polarized light this stereoisomer will rotate, and that is called specific rotation. And what is that? So in this we use this equation where alpha is observed rotation as per the polarimeter, concentration must be present in grams per ml, and liter should be the length of, L should be the length of sample, which must be in decimeters. So if you use these parameters, then you can get this equation to use and get your specific rotation. So if everyone uses the same parameters, you will always have the exact same specific rotation. So any given enantiomer or diastereomer or stereochemically active molecule will have a specific rotation, and with that value you can kind of identify, as I told you that we could do with RF value in practical 2. So RF value is also retardation factor of your DLC. I told you that this is standard if everyone uses it on same condition. So similarly, the specific rotation will also be constant if everyone uses the same parameters, right? I know that we are studying organic chemistry, so there are not many numerical questions that I practice with you. I did a few in some of the previous lectures, but this is a simple equation and you can expect a simple numerical question in your exam. Right? You will be given 2 or 3 values and the rest of the value you will need to remember. So it's a good idea to memorize this small and simple equation. Yeah? Right, so now we are moving towards identifying that what relationships could different stereoisomers can have with one another. And in doing so, tetrahedral structure could be useful, but Fisher projection structure could be really useful. So now we will try to learn how we can make Fisher projection, what Fisher projection is about, and you will see that this will become very useful in identifying when you are given 2 examples of compounds and asked that what relationship do they have with each other. So we can do that easily with the help of Fisher projection. So Fisher projection is a flat representation of the 3D molecule or the tetrahedral structure. A chiral carbon is at the intersection of the horizontal and vertical lines. So if this is your tetrahedral structure, you can just consider that you are viewing the molecule from this angle, which is between out of the plane and on the plane. So if you will consider this here, then these two will be horizontal and these two will be vertical, right? And Fisher projection tells that the vertical groups will be inside the plane always, and horizontal groups will be outside the plane always. So if you have a picture like this, you don't need to draw the wedges for inside the plane and outside the plane. This simply tells that both of them are outside the plane and both of them are inside the plane. And how we converted that into this? This is particular way that you have to look at the molecule. Then the 2 groups will become horizontal and the other 2 groups will become vertical. So we have a cross of a structure in Fisher projection for any given molecule. Now imagine if you have multiple chiral centers in a molecule, how difficult would it be to draw all the wedges, the dotted and solid wedges? So Fisher projection is the shorthand representation of all the chiral molecules. Right? Any question? Easy, right? So this is trying to help you to tell the relationship between different isomers later, which we will see in a while. The first thing is that how can we draw the structure? Right, I will also give you one trick here which I learned during my study time because I was sometimes getting confused between these two. So what you can do is you can put RNS for this one, which you already know, and then you can make a plus and put groups according to where it becomes RNS. So if this was R, then you have to put groups here according to that this also becomes R. Or if this was S, then you can put the groups in order to make it S. That was a bit helpful for me, and we will definitely look at an example when we are doing the RSN configuration, probably in next few slides. Right, well, this is R propane anyway, 1,2-diol. So how this is R? 1, 2, 3. Right? 1, 2, 2, 2 to 3 is anti-clockwise. So this should be S. But hydrogen is horizontal, which means it's above the plane. So we have to reverse our answer. So this will be R. Right? Now check here. 1, 2, 3. Clockwise. Hydrogen is on the plane. 1, 2, 3. Clockwise, right? 1, 2, 3. Clockwise, yes. So hydrogen is on the plane. You have to switch it with this group. So then this will come here. That will go there. So it will be 1, 2, 3. Clockwise. And since you have made a switch, it should be S. There's some mistake on this slide. I will get back to you. Let me do it again. 1, 2, 3. Anti-clockwise. R. Perfect. 1, 2, 3. Oh, you have to switch as well. So this goes here, this goes here. So 1, 2, 3. S, R, yeah, correct. There's no mistake here. I was wrong the first time. So that is still R, right? So what I was saying, that the shortened trick would be, if you are struggling with making the Fisher projection, check the configuration first, and then put these groups according to R or S. Do you get this point? Otherwise, it's the rule that you have to follow this angle, and these two groups will be horizontal, and the other groups will be vertical, right? And what's the difference between vertical and horizontal? Verticals are outside the plane, always, and verticals are inside the plane, and horizontals are outside the plane. Yeah? Yeah, just like that. Vertical are inside, horizontal are outside. Yeah. Right, so another example, always between 1 and 4, because 4 is outside the plane apparently, and 1 is on the plane. So we look at here, so 1 and 4 will become horizontal, that means 2 and 3 will be vertical. Right? Here again, these two will be horizontal, just like that, and then these two will be vertical, just like that. Easy, right? Correct? Right? Okay. And then S is still S. Right? If we wrongfully put hydroxyl here and H there, then this will not be S anymore. Right? That will be the other enantiomer, R. You can try it. So right now this is 1, 2, 3, R, but it should be S because hydrogen is horizontal. Now put it on the other side. So hydroxyl will be here. 1, 2, 3. S and then R. Because we have switched. Right? What I'm saying is I want you to draw this structure and replace hydrogen with hydroxyl. Just that way. So if this isomer is S, then the other one which I'm asking you to draw would be R. So you could do this mistake when you are trying to draw the Fisher projection from 3D structure. So it's always good idea to check the configuration in both cases. Then you will never be wrong. If this was R, then your Fisher projection should also be R. If this was S, then your Fisher projection should also be S. Do you get this point? So the only problem you can have here is where to put hydroxyl, right? You could have put it wrongly on the right hand side, but that will convert the S from R and S from R or R from S. The other way around. Right? Okay, so when you are writing your Fisher rules or your Fisher projection, these are the points of configuration. First is that the carbon chain is on the vertical line. The longest carbon chain which you will see in the molecule, that will always be in the vertical line. Second thing, the highest oxidized carbon would always be placed at the top of that vertical line. When I say oxidized, that means the functional group which has more oxygen generally speaking. So like carboxylic acid or aldehyde or ketone or those things. Finally, the rotation of 180 degree, it will not change the molecule, but if you rotate the 90 degree or replace the groups which are at perpendicular from each other, that will change the stereochemistry. Because horizontal and horizontal, left hand side or right hand side, both of them are on the same side because both of them are outside the plane. Well, vertical ones, it doesn't matter if you convert them like that, like rotate 180 degrees, they will not make any difference. But if you change it with the horizontal ones, it will not be allowed, meaning that will change the course of the stereochemistry in that projection. Right? So what I am saying is, if this is the structure, it doesn't matter that if you put this group down and this group up, that will not make any difference. Or you can put this group there, or this group there, or this group there, or that group there. So 180 like this or like that will not make any difference. But 90 degrees, if you switch them, or them, or them, or them, that will change the course of your stereoisomer. Because horizontal and vertical, both of them are on the same plane, either outside of the plane or inside of the plane. So you cannot simply replace them with each other. That's the whole point of this slide. Are you able to see this? Why that is not possible? Because they are on the same plane, and they are on the same plane. So 180 will still bring them on the same side. But 90 will change them from inside to outside and outside to inside. Right? Correct. So now, as we have seen the rules that, the longest chain should be where and the most oxidized group should be where, right? As per the previous slide, that the longest carbon chain must be vertical. So you see 1, 2, 3, 4 carbons are all in vertical line. Now these groups can be changed according to RNS. So if you are given an example in exam, and for any other test that you are supposed to give the RNS configuration, then you don't have to do a lot of switching. And you don't have to remember all the previous rules, because hydrogen will almost always be horizontal. And horizontal means outside the plane. So you can simply tell the rotation and reverse your answer. Because hydrogen is horizontal, and horizontal means outside the plane. So when hydrogen is outside the plane, you have to reverse your answer, right? As per the previous rules as well. So in this case, hydrogen which is horizontal, and horizontal simply means outside the plane. So it will be simpler. And this is 1, this whole group will be 2, this will be 3. So 1 to 2 will be 3. It's clockwise. But hydrogen is horizontal, that means outside the plane, so you'll have to reverse your answer. So this will be an S. So in Fisher projection, you can simply remember that clockwise is S and anti-clockwise is R. Because of the fact that hydrogen will almost never be vertical, it will always be horizontal. Right? Do you see this point, or it is too overwhelming at this point? So why are we studying this Fisher projection? We were happy with the 3D structure, right? The tetrahedral structure. So we saw in our previous chapter or lecture, same chapter, but yeah, previous lecture, that when we are talking about tetrahedral structure, there are 3 cases. Either hydrogen is behind the plane, or it is above the plane, or it is on the plane. And in all those 3 cases, we had different rules about RNS configuration, which we also revised earlier today. Right? But in Fischer projection, hydrogen will always be horizontal. That's why I said that Fischer projection helps us in identifying the relationship between different stereoisomers, as well as it simplifies the assignment of R and S, because we don't have to remember all those three rules. Just one rule is enough here, that since hydrogen is outside the plane, so clockwise will mean S and anti-clockwise would mean R when we are talking about Fischer projection. Right, so this is giving us help about two very important factors in stereochemistry. One is assignment of R and S configuration, and second, what relationship the molecule have with its mirror image or another isomer. So that's why Fischer projection is super important. Yeah. Right, now this molecule has two stereocenters. So first one we already checked. Second one, let's check again. So 1, this whole group has 2. This is 3. So 1, 2, 3 is clockwise. But then clockwise is what? S. So S. Right? Now we don't need to memorize those three rules. So if in exam you are given tetrahedral structure and you can't remember the rules, you can change it to Fischer projection and still give your answer. But if you are more comfortable with that, by all means, yeah. We need to learn both of them to ace our stereochemistry lesson. Right. These are the relationships which stereoisomers can have with each other. So the one was enantiomer before, which we saw, that the molecule which has a mirror image relationship with the other molecule, so they would be called enantiomers. So diastereomers are the molecules which do not have the mirror image relationship with each other. But then both of them are isomers of each other based on some other factors. So one of that important factor in diastereomers is carbon-carbon double bond. So you remember cis and trans from carbon-carbon double bond, right? So cis and trans are a perfect example of diastereomer. Because if you put a mirror there, then this molecule is not a mirror image of that molecule, right? So that's why they are called diastereomers. Okay? Right. Let's look at a little bit more complicated example. So may I have your attention? These questions are super important for exams as well. And then of course we will practice more in our tutorial session. But if you are with me, I will also give you one hint right here. That if this is a question in exam, you are given these three structures and asked what is the relationship between all three of them, then what you need to do is you have to compare them one by one with each other. So let's compare these two. What difference do you see between these two? What difference do you see between these two? So you are saying that this is flip of that molecule. You would be right. You would be right. But flipping, can it superimpose on the original molecule or not? Now remember that this up means outside the plane and this down means inside the plane. So if this group was inside the plane and now you are flipping it, so this will become outside the plane. So this means that both of them will not be superimposable on each other, right? That makes them what? That's the definition of enantiomer. That the mirror images of each other, which are non-superimposable on each other, are called enantiomers. Right? And when they have no mirror image relationship between each other, then they would be called diastereomers. So these two are enantiomers of each other. And then this to that or this to that will be diastereomers of each other because they are not mirror image of each other, right? Here this is up, this is down. Here this is down, this is still down. So not completely opposite of each other. Now mind my words here. What did I say? That they are not completely opposite of each other. Well, in the case of enantiomers, you can easily identify them because they will be exactly opposite of each other. So when all the stereocarbons are opposite in two examples, those two will be enantiomers to each other. And when all of them are not opposite, then they will be diastereomers with each other. Now look at them again. At this carbon, above. This carbon, below. So opposite, right? At this carbon, below. At this carbon, above. So exactly opposite of each other. That makes them enantiomers. Now compare this with that. Down, down. So same. One is same. Other one is opposite. That means that they are not completely opposite of each other, right? Diastereomers. You can also compare these two. So down, down, up, down. So not completely opposite of each other, right? So any one of them has a diastereomeric relationship with this structure. And then the two of them have enantiomeric relationship between each other. Can I get some head nodding? This is super important. Do you want me to repeat this? Has anyone understood what I have been saying for last 30 seconds? That's what I need. Just the last 30 seconds. Right? So for molecules to be enantiomers with each other, they need to be completely opposite of each other. Like we saw here. Up, down, down, up. Completely opposite, right? At both positions. So these two are enantiomers. If they are not completely opposite to each other, one of them is same and other is opposite, it doesn't matter. Because they are not completely opposite to each other, then they will be diastereomers with each other. Right? Awesome. Thank you. Right, again. So this and this are enantiomers to each other because right, left, right, left. If you rotate, it will appear that they will align with each other, but you know they will not because outside the plane, inside the plane. And if you compare them with them, they will be diastereomers. And how you can easily tell this? Because here they are exactly opposite. Right, right, left, left. Opposite of each other. Here, no. One is reverse, but other one is same. Right? Or opposite, same. So any one of these will be diastereomer of any one of these. But if you compare them together, these two are a pair of enantiomer, these two are a pair of enantiomer, and how you can tell? Because they are exactly opposite of each other. Make sense, right? Very, very, very important for your exam. Right, so in case of diastereomers, which will generally have more than one stereo centers or chiral centers or asymmetric carbons, whatever you want to call them, sometimes we can also have plane of symmetry. And that will make the overall molecule as non-stereoactive, meaning that if you put that in polarimeter, it will not rotate the plane polarized light at all, even though it had more than one chiral center in the molecule. But even then the molecule can have plane of symmetry or center of symmetry, and those molecules are called mesocompounds. So mesocompounds are, technically speaking, the cases when the simple rotation will get to the same molecule because they are not chiral anymore. So chiral molecules are handedness one, and in those cases the rotation will not give you the superimposable structure, right? But in case of any element of symmetry, such as plane of symmetry or center of symmetry, the superimposable thing will be quite possible. And how we can tell that? In a structure, that if the structure has a plane of symmetry, just like in this case. So you see that this pink line, it's pink, right? Okay. Pink line is dividing the molecule in two equal parts, which are exactly same. This is down, meaning both of them inside the plane. So, because of this plane of symmetry, this molecule is not stereochemically active anymore. However, they still have chiral center. This is a chiral center, right? This is a chiral center because they are attached to 4 different groups. But because of plane of symmetry, the overall molecule will not be stereochemically active, and they are called meso compounds. Okay? Another example. Right, so I want you to also note down these things which I am going to say right now. You like to write, then you can write. If you don't like to write, then I can probably send a voice note right now. Right, voice note there. Let me think of it what I'm going to say. Right, so in Fisher projection, when the top and bottom are same, and both the groups are on the same side, then they will do the same. Alright, basic biochemistry. Alright. Hello students. So we are learning stereochemistry right now. And I want you to remember this point, that when you have a Fisher projection, and the top and bottom of molecule is same, and then the groups which are present on horizontal lines are also same, then they will always be mesocompounds. Thank you. Right? So this is a trick. You don't have to think about it. Once you see that the top and bottom are the same, and the groups are on the same side, then there will be meso. Right? And this symmetry, of course, is making them to be able to superimpose on their mirror image. That's the concept of plane of symmetry. Or in simple words, it's dissecting the molecule into exactly equal parts. Right? Right, so another equation which tells us that for any given molecule, how many stereoisomers are possible. So that equation is 2 to the power n, where n could be the number of chiral centers which are present in that molecule. So imagine if a molecule has 1 chiral center, then you will put 2 to the power 1. That would mean that only 2 stereoisomers are possible for that molecule. And those will be enantiomers to each other. Right? One would be R, other would be S. So both of them are stereoactive. Right? Imagine if the molecule has 2 chiral centers. Chiral center means what? Asymmetric carbon, the one which is attached to 4 different groups. If a molecule has 2 asymmetric carbons, that would mean that it will have 4 possible stereoisomers, 2 pairs of enantiomers. Just the examples which we saw earlier, right? 2 pairs of enantiomers. Why? Because 2 chiral centers. So if you use this equation, you can know that how many sets of stereoisomers we can have for any given molecule. Right? Very simple equation. 2 to the power n, where n is what? Number of chiral centers. Right? Alright, let's take an example. If the molecule is 2,3,4-trihydroxybutanol, then you will draw it and you will see that it has 2 chiral centers. 2 chiral center will mean that you will have 4 isomers. That means you'll have to make 2 pairs of enantiomers. This exact question was there, I think, in last year exam. So this is that important. You are given a name, asked to draw the structure, and tell and draw how many isomers do you see there in terms of stereochemistry. Okay? So here it is. That is a pair of enantiomer. This is a pair of enantiomer. And if you compare anyone with each other, they will be what? Diastereomers, right? Right, another example. Now you remember that the top and bottom are same. So meso, right? But in there, the groups are on opposite sides. So there must be meso. Right? Are you able to see? That was about the message which I recorded just now. Top and bottom are same, and the groups are of the same side. So these two become meso. This means that you can rotate this molecule and they will be superimposable on each other. Yes.
What's the plus minus?
Plus minus means meso. In this case. Plus minus means that it will not rotate the light to left or right. Because they are not stereochemically active anymore. That's what I said, right? Meso compounds, because of the plane of symmetry, are not stereochemically active. Plus minus could be either meso or it could be racemic mixture. Racemic mixture, you remember that the mixture of both plus and minus stereomers in equal concentration. Right. I think you are getting confused a little bit. Let me take you back a little while. So dextrorotatory and levorotatory, those are plus and minus. So for nomenclature, we either write R or S with the name or plus or minus with the name. So when we write plus minus together, it means that either one of them or a mixture of them. That's what I said, either meso or racemic mixture. Plus, minus, diastereomer. So one of them is plus, other one is minus. If they are together in equal concentration, then racemic mixture. If they are in this form, then they are meso. So in both cases, you can write them as plus minus together. That means you are not specifying which one is plus, which one is minus, because you can't. Those are experimental terms, remember? But yeah, with name you can write, for example, if this one is R and this one is S, then you can write this is, oh, this is R and S. So this is R and R, sorry. So you see 2R, 3R. This one is 2S, 3S. So, exactly opposite of each other. See? Now this one is 2R, 3S and 2S, 3R. So they are also exactly opposite of each other. But because of plane of symmetry, they become meso. And plus minus only tells that we are not specifying which one is what. They could be present in a mixture. Or in this form also we can write plus minus. So meso are not stereochemically active anymore because of the plane of symmetry. Right? Maybe one last example. Right, so dihydroxybutane diuric acid or tartaric acid. So this is the structure of tartaric acid. Then these two are meso because why? Top and bottom are same and groups are on same side. So that's why we have plane of symmetry here. Right? So that one would be plus minus isomer of tartaric acid. But any one of these could be plus and the other one would be minus. Of course, we can't tell just by looking at structure because those are experimental terms. Right? Also, one thing you notice, I told you, right, that enantiomers will be exactly opposite of each other. See? 2R, 3R, and the enantiomer is 2S, 3S. So exactly opposite. R, S. R, S. Similarly here, 2R. So it's 2S. 3S, 3R. So exactly opposite of each other, right? If you compare this with that, or this with that, So enantiomers are exactly opposite of each other, right? Okay, just two more examples to see what type of physical properties can we expect from different stereoisomers. How drastically different they could be from each other. So this is an example from recent literature that even though they only differ on the basis of small stereochemical differences, like this group is outside the plane, inside the plane, inside the plane, outside the plane. But they're this one that are same actually. So this is enantiomer and that is enantiomer. We can compare this with this, or this with this. So this is one of the enantiomer. This is the opposite enantiomer. That's what it is. So you see that the pair of enantiomers have a difference between melting point as 141 degrees and 98 degrees. So this in the case of cis epoxide when both the groups are on the same side, right? And this in the case of trans epoxide when both of them are on the opposite side. Epoxide is this way. Don't be intimidated by the name. These are simple cyclic ethers. So ethers are COC, right? They are COC but in cyclic form. So they are called epoxide. Not important. The name is not important. But you can see that the different stereoisomers have so much difference in terms of their melting point. I want you to consider that if you were doing a reaction and in your reaction you are forming both these sets of enantiomers, how do you think you can separate them? Temperature, right? So one will melt at 100 degrees, the other one will melt at 140 degrees. So you can just heat the mixture. The first one to melt, you can separate it because that will be liquid. The remaining solid will be your other enantiomer. So that will be physical resolution. Right? You are separating the mixture of enantiomers from each other, hence resolution. But you are doing it physically on the basis of temperature, physical resolution. Just an example. Right, the final example is here. This is meso stereoisomer and this is chiral stereoisomer. The solubility for chiral one is 0.1 gram per 100 ml ethanol, while for meso is 3.3 grams. So you will add enough ethanol, this will readily dissolve, that will still remain in your solution, you can filter it out. So another example of physical resolution on the basis of solubility. Because this one is dissolving 3 grams per ml, that one is only dissolving 0.1 gram per ml. Of course it will not be 100% foolproof, but still you will be able to at least isolate one of them very easily. Right? Any question? This will be the end of this chapter. So what we have covered overall: RNS configuration, Fischer projection, and enantiomers and diastereomers and mesomers. These are the three take-home messages or highlights of this chapter. And let me remind you once again, super important all of that. So please do not miss out your tutorial session this week. That would also happen to be my last one. Right, let's take a quick break of 5 minutes then before we start our next chapter. Yes.
是 OK。是那个。
Let's go, you ready?
No. Hi. Hey, are you still recording?
Yes.
Oh my god, you still recording? Cannot. That is evidence against me. Sorry.
Okay, then we go out group meeting. Then we go out meeting. No, yeah. 你出了先，你出了先。好帅你哦。
再来看多一次。对众生，我拿不到我的分。我还没有。
Can I tell you? Like legit. I give up in
我拿笔不是傻吧？
Can I tell you? Let me get. You haven't get a pen. You haven't even get a pen. One second.可是这个很吵吗？它很吵，超级吵，已经吵到。可以回去。要做很多设置工作，你别吵。所以你知道 ，sorry， 所以你知道举。有味道吧？我问了味道。哦，所以黄这样子的那个是。然后我们是，因为我们问了味道完，然后我们忘记那个。做那个皮儿，那个是有那种像来那种臭那种黄牛的味道。
My teddy bear. I mean my another teddy bear.
Just kidding，不要打我。
The one that.
I'm listening. I know the whole story.
Chapter 6, 5 minutes are over. Right? Right, so chapter 6 is one of the easier chapters. If we are lucky, we can finish it today so that the next lecture will be only about one chapter. Right? And since the next lecture will most probably be done online, so that's why I have rescheduled things a little bit. Right, so this chapter is about the study of chemical reactions and mechanisms. The learning objectives in this chapter will be to be able to identify different types of reactions. And when we say different types of reactions, that would mean different types of mechanisms, because the progress of reaction is studied by its mechanism. Then we also want to be able to develop some expertise about explaining or suggesting the mechanism of a given reaction. So how can we do that? And finally, we will use some principles of thermodynamics and kinetics of a reaction to predict the progress of the reaction. These three things are the overall learning objectives in this chapter. Right, so now there will be a lot of slides where I will be moving like my button here very quickly, because I take credit in it, that I have summarized them really well. And if you will just keep your eyes open, you will understand them really easy. Right? I'll sit down here, but yeah, do not be intimidated by my words. If you need to stop me anywhere to ask questions, go ahead. Right? So all organic reactions generally can be classified in these four types. Right? There are hundreds of reactions about any given functional group. That's what we have been doing for so long, right? We studied reactions of alkanes, of alkenes, of alkynes, of aromatic compounds, and then so we'll continue for other functional groups as well. But then these four are the types of reactions which all those reactions are all about. So substitution reaction, as the name suggests, something gets substituted. Addition reaction, something gets added. Elimination reaction, something gets eliminated. And rearrangement reaction, some rearrangement happens. Right? So no difficult things in them. Next few slides, I will have the definitions there and few examples. That's all. So probably I can just be silent for a while, and then you can see what I'm doing. Right? So substitution reaction are characteristics of alkanes and alkalides and aromatic compounds. So this slide will be useful. If you can only remember this slide, then you can write, reactions for all three of them. Just any substitution reaction. Right? Example, chlorine is there. Sodium hydroxide is substituting chlorine. So you see a substitution reaction, right? Second type would be addition reaction. So addition would mean that a smaller molecule will add up in the starting material, right? So they are characteristic reactions of compounds with multiple bonds, such as alkenes and alkynes. So again, this slide will be important. If you know this information, then you already know a lot of reactions for alkenes and alkynes and aromatic compounds, because they have multiple bonds. Right? Easy, right? We have studied this. Elimination reaction, something, breaks off the molecule. They are definitely opposite of addition reaction, and they are important to actually make multiple bonds. Right? So addition reaction was characteristic of multiple bond compounds. But if you want to make multiple bond compounds, you can use elimination reaction. Right? So addition reaction and elimination reaction are simply opposite of each other, right? We have looked at this example before. You see that hydrogen and bromine is being removed, and as a result you get carbon-carbon double bond. Rearrangement reaction. So nothing breaks, nothing forms, just some groups change their positions in most of the rearrangement reactions. We will not see many examples of rearrangement reactions in our course, but here is one if you want to see. So this is the reaction in which terminal alkene gets converted into middle alkene. So you see that the carbon-carbon double bond initially was at the last carbon. Now this carbon-carbon double bond gets shifted here, and then methyl comes there. So rearrangement of double bond and methyl group to make it into tetra-substituted alkene. Classic example of rearrangement reaction. Very simple. I have performed this in actual lab as well. All you have to do is just take this terminal alkene, add acid, heat a little bit, at the end you will get this gas complete. So methyl group has moved and carbon-carbon double bond has moved. Right? So that's why it is a rearrangement reaction. The other thing we need to consider about the mechanism, so these types of reactions, they have different mechanism altogether. That's why they are different types of reactions, right? So there is one more thing beside types or classification of reaction when you are working about types or mechanism of reaction is how the bond breaks. So there are two ways any bond can break. Either hydrolysis or homolysis. So hydrolysis will make charges like anion, cation, meaning electrophile or nucleophile, or with hemolysis meaning that they can make free radicals. They don't take the whole pair, but both atoms which were bonded together will take away one electron each. So that makes them free radicals, right? Example of hydrolysis will be the formation of ions, like electrophiles and nucleophiles. So hydrolysis gives rise to ionic reaction, right? One of them will take away the whole pair, and the one which took the pair will get the negative charge, and the other one will get positive charge. So you see that we are getting ions. One is nucleophile, which is negatively charged. Positive charge will be electrophile, right? In hemolysis, we don't have this clear segregation of ions. So instead we get radicals, free radicals. And you could also observe the change in arrows. So for free radical formation or homolysis, we are making these fishhook arrows. We are not making the regular two-sided head of the arrow. So keep this in mind. When you are drawing mechanism with free radical reaction, then you'll have to use fishhook arrows. And we get two free radicals. Now free radicals are not charged. even though they have extra electron, but just one electron, and they are very, very unstable. Ions, you can add the counter ions and capture them easily, and they can do electrophilic and nucleophilic substitution quite delayed as well if you want them to be. But free radicals are very unstable. They will react with almost everything and anything. Right, so let's look at some of the important anions and cations of free radicals. So when we do this, we get carbocation. Carbocation has been very important already, right? Almost in every chapter we see some discussion about carbocation, because carbon can be attached to the elements which can have higher electronegativity than carbon, which is indicated here as Z, meaning that it has high electronegativity, as obvious from the partial negative charge on it. So when this bond will break, carbon will attain the positive charge, hence the formation of carbocation will occur. Right? In some cases, we can also form carbanion, meaning in which the carbon will retain a negative charge. And that will be only possible when the atom which was attached to carbon was partially positive, meaning that it has even lesser electronegativity than the carbon. So in those cases when this bond will break, carbon will attain a negative charge, and that anion is called carbanion. This is also quite common, not for the sake of our syllabus, but for generally speaking. For our syllabus, carbocation is the most important intermediate of carbon, but carbanion is quite common in many reactions as well. Right, so electrophiles are what? Electron-loving moieties, which seek electron. So they can have positive charge, or they can also be called as Lewis acids because they can accept a pair of electrons. So Lewis acid by definition are compounds which can accept a pair of electrons. So electrophiles are, technically speaking, Lewis acids. So they can accept a pair from Lewis base, which by definition are compounds which can give away a pair of electrons, or can also be called nucleophile because they have extra electrons and they would want to seek nucleus which is positively charged. So that's why the name nucleophile. So carbocation, which is a Lewis acid, can react with a base such as Lewis base. So you see the direction of electrons? So these curly arrows are not same as equation arrows that we make. So when we are writing equations, we write a straight arrow. When we are writing mechanisms, we need to draw these curly arrows for showing the movement of electrons. And please do not mess up with this sequence. Always, 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 you will move electrons from where electrons are to where electrons aren't. You cannot draw this arrow the other way around, that would be wrong. Even though we will say sometimes that electrophile is attacking on base, but when you actually draw a mechanism, you will have to put tail of the curly arrow towards the nucleophile and head of the curly arrow towards the electrophile. This makes sense? Because that's where electrons are moving from, and that's where electrons are moving towards. So the head shows that electrons are moving in this direction. Yeah? And as a result, this bond will form. Easy peasy. Right? In some cases, even if they don't have the obvious positive charge, they can have partial positive charge. they can react with so many Lewis bases or nucleophiles, such as this one. So carbonyl carbon is an example of carbon which does not have a positive charge yet, but because of oxygen high electronegativity, it is kind of partial positive and it can accept the attack of nucleophile. So these are characteristic reactions of carbonyl compounds, which you will see later in the chapter of carbonyl compounds. But here, for example, you can tell, right, that this carbon is quite electropositive because of the presence of oxygen. Hence, this carbon is electrophilic. That's what we can call it, right? And therefore, the Lewis base or the nucleophile can attack on this carbon, and as a result, you can get alcohols from this reaction quite readily, right? So a nucleophile is a Lewis base that seeks positive center, hence the name nucleophile. Phile means cinephile, like I like to watch movies, so I would be called cinephile. So nucleophiles are the ones which like nuclear. So that's why they are negatively charged and they would like to attain positive charge. And nucleus is positive charge, right? Then for the example of substitution reaction, we looked at earlier nucleophilic substitution reaction, right? So nucleophilic substitution reaction in which a nucleophile is substituting the other group in the given compound. So that's why they are called nucleophilic substitution reaction. Right, so nucleophile will attack on carbon where leaving group will leave and nucleophile will substitute the leaving group. This will be an example of nucleophilic substitution reaction. Okay? Right? So the examples of all the types of reaction, the one which we have seen so far, are SN1 and SN2 reaction, which are nucleophilic substitution reaction 1, nucleophilic substitution reaction 2. E1 and E2 mechanism, meaning elimination reaction 1, elimination reaction 2. We have also seen that. Addition reaction on alkenes and alkynes. We have seen that. We have seen bromination of alkene. We have seen hydrohalogenation of alkene. Similarly, we have seen bromination of alkyne, hydrohalogenation of alkyne, right? We have also seen mechanism of electrophilic aromatic substitution, just in our previous lecture. Remember? Friedel-Crafts alkylation, Friedel-Crafts acylation, and then bromination, sulfonation, nitration, all those reactions where we saw that the electrophile substituted the hydrogen of benzene ring. Hence, electrophilic aromatic substitution reaction. Right? And then rearrangement, as I said, you will not see many examples, but stay tuned for the remaining chapter, you might see one or two. And then one generic example we saw earlier today, right? Right, so the last part of this chapter is about thermodynamic and kinetics. So when we say any reaction is happening just like that reactants are getting converted into products, two things are important: the thermodynamics of the reaction, which tells us that if this reaction is possible or not. In simple words, thermodynamics tells that the energy demand of the reaction, it makes sense or it doesn't. If it makes sense, then reaction can happen. If it doesn't make sense, it requires tremendous amount of energy or it will release tremendous amount of energy, then most probably those reactions will not be very, very feasible. Kinetics of the reaction tells that if a reaction is supposed to happen, how slow or fast that reaction will happen. So kinetics is about speed of reaction and thermodynamics is about the energy demand of the reaction. Right? So these two factors are important to consider when you are looking at any given reaction. Well, mechanism of a reaction gives us the stepwise details of the progress of that reaction. That how this reaction would have proceeded in terms of the movement of electrons, what intermediate could have been formed in this reaction, what type of reaction could have happened. So all those details we can tell with the help of a chemical reaction. So altogether, when any reaction is happening just like that, in an equation, the reactants are getting converted into product, these three factors are essential to be considered. Yeah? So there are many theories about the progress of reaction or why reaction happen or what drives the process of a reaction. I have highlighted three of them here, which are quite simple, and that makes a lot of sense to me. In other textbooks, you can find other theories as well. So I never say that these are all the comprehensive list. But I want you to get introduced with them so that you can explain to some extent that why reactions happen or what drives a reaction. So number one is called collision theory. Number two is charge theory. And third is molecular orbital theory. So collision theory is about the activation energy of a reaction. So it says that reaction will only happen when the collision of the molecules generate a threshold of energy which is required for the reaction to start. So when molecules will collide with each other, they will transfer energy from one place to another place, right? So those transfer of energy need to reach a certain threshold after which the reaction could happen. If they don't reach to that level, then the reaction will not proceed. And that threshold of level is called activation energy. So this is what collision theory says. Charge theory simply says that, partial positive, partial negative, negative, positive, they have electrostatic attractions or repulsions with each other. So they will align themselves according to charges, and if they have enough strength to make a bond with each other, they will make a bond. If they don't have enough strength, meaning in terms of the attraction and repulsion, then they will not make a bond. Right? And then of course molecular orbital theory tells us about the orientation of orbitals, the formation of new hybrid orbitals, and all those things are covered in molecular orbital theory. So I have tried to, this is taken from the book, Clayton, the four other books that I shared with you. So you see that in collision theory, what can be said that molecules will collide, they will impact with each other. After impact, they will go away from each other. So in these collisions, they will generate energy or they will transfer energy from one to another. Right? If the outcome of these collisions reaches to the threshold which is activation energy, then they will make bond. If not, then they will just go away from each other even after collision. So that's the simple explanation of collision theory. Simple example, if we have this molecule and that molecule, then if this partial negative and this partial positive can attract each other with enough force, then they will attack on each other and form a bond. If they can't, doesn't matter, you can keep increasing their concentration, nothing will happen. Right? And then molecular orbital theory, of course, nucleophiles, electrophiles. If the difference in the energy orbitals are not that much, reaction can happen. If the difference is little, something can happen, but the difference is too much, then nothing can happen. All it needs to do is transfer these electrons through there. That's what it needs to do, right? In terms of the molecular orbital theory explanation. But the difference in the energy, it needs to be derived from somewhere. Either from providing it in terms of heat or pressure or something which can increase the overall energy of the reactants, which can be further converted into something else. Right? Let's talk about mechanism a little bit before we begin to the thermodynamics and kinetics equations. So I want you to take a moment to look at these points. This is taken from all my experience of writing mechanisms and doing reactions for more than 10 years in labs. This is my summary. You will not find it in books. So these points to remember when you are writing the mechanism. First, what is the energy demand of the reaction? Why are you trying to react something with the other thing? Will it increase the energy of the product? Will it decrease the energy of the product? First of all, think of that. Are you making stable molecules or are you making unstable molecules in a proposed reaction? So if the energy demand is not working out with logic, probably the reaction will not happen. Unimolecular or bimolecular steps. This is also important to know that in any reaction, when you break down the reaction in multiple steps, then how many molecules are involved in each of these steps? If you don't know that, the catalyst is involved in the first step or second step or third step, you will not be able to make sense of the mechanism or movement of electrons. So it's trivial information that you should know that what is more reactive, what is less reactive. The more reactive things will react faster, meaning that the first or second step. The less reactive things will only react later. Right? Weak bonds are generally broken in a reaction and strong bonds are formed. You should know which bonds are weak, which bonds are strong, right? Based on the difference in electronegativity, of course. Know your electrophiles, nucleophiles, acids and bases. Super important point. All the mechanism is based on this point. If you mess up that which one is electrophile, which one is nucleophile, then it doesn't matter. You can move electrons all day, but you will never make logical mechanism. So some trivia: Lewis acids are what? Electrophiles. Lewis bases are what? Nucleophiles. And then the normal acids like sulfuric acid, we call them protonic acids, right? They will provide proton. So proton is H positive, right? So H positive means that the most of the reactions intermediate will also be positive. Because if any negative thing will form, the proton will go there and it will neutralize. Right? So if you are doing a reaction in an acid catalyst, then your intermediate will be positively charged. If you are doing a reaction in basic medium like sodium hydroxide or other bases, then your intermediates will be negatively charged. Because if your intermediate is positively charged, hydroxyl will trap it and it will neutralize it. Right? And then finally start moving electrons from where there are more electrons to where there are less electrons. There is no right or wrong. You can have as many steps and just try to move electrons from one point to another point and take it to see what will happen if you move from here to there and then there to there. But then, of course, this is for practice, but once you will get more expertise in this, then you will see that some of them are unnecessary steps. You have been simply moving electrons to just come back to the same point later. So this could happen. So once you are practicing, it's okay, you can make as many steps. But later, once you are a little bit more expert, then you can minimize the number of steps in the mechanism. So if you consider all these points, I am sure that you can easily draw the mechanism of any given reaction. Right? Now, this is a classic example again from the same book. This reaction is called Cannizzaro reaction, which is not important. You don't need to remember the name. But what is happening in this reaction? That this molecule is being converted into those two molecules. Right? So this aldehyde is converting into carboxylic acid as well as alcohol. Right? So this reaction is called Cannizzaro reaction for some reason. Probably the guy's name was Cannizzaro. So what we are trying to discuss here is that how do we actually determine the mechanism of the reaction? Right? We can propose anything in a piece of paper. That doesn't mean that this is the exact way by which that reaction happens. So how do we know that exactly how a reaction happened? We can also determine that on the basis of experimentation. Otherwise, we can say that this is a proposed mechanism. If you want to say that this is the exact mechanism, we need the experimental proof. And one example by which people studied Canizaro's actual mechanism was by doing the radioisotope labeling. So this is a chemical technique in which you can put a specific radioisotope of any element, and then you can track that using an instrument called ESI, electron spin resonance machine, or spectroscopy. So with that, you can tell that the specific isotope has ended up in which part of the molecule. And then you can tell that what could have been the intermediate of that reaction. Now, here are examples of different mechanisms of Canizaro reaction. Same reaction, but if you notice, then you will see that in all these reactions, the intermediates are different. And you can note down that all mechanisms are very, very logical. There is nothing wrong with any one of them. See, in mechanism A, the base is attacking the nucleophile perfectly well. O is getting negative charge, then the negative charge comes back to the oxygen, and hydrogen shifts to the next molecule. Yeah, this is the same compound but different molecule. And as a result, one of them gets oxidized and the other one gets, reduced. That is the definition of Canizaro reaction. There is nothing wrong with this mechanism, but you see that what is the intermediate of this reaction? The O negative anion, right? Let's look at second example. So in second example, again similar attack, but instead of this step, in here, this negative charge now attacks the electrophile. And as a result, we get this dimeric adduct as a intermediate. There's nothing wrong with this. Still we are getting the same product. But which one of them is correct? How would we know? There's only one way to find out. Do the experiment. So that's what people do. The exact mechanism of a reaction is determined experimentally. That is the whole case which I'm trying to make here. So when they did the experiment, they found that they have put oxygen 18 isotope in the base molecule to see that where the O will end up in. So then they found that the base actually was present in the aldehyde part. Right? So aldehyde, aldehyde. So with that, if you'll start, then you will know where the things are happening. So the actual mechanism was formed on the basis of experimental information which tells us that this reaction occurs by formation of a dianion where two oxygens will get a negative charge. Now all this detail is very unimportant for your syllabus, but with this example I am only trying to tell you that how the mechanism is determined. I am not asking you to just remember all these three different possible mechanisms. That is super unimportant. But with this example, you can tell that how much effort goes into finding the actual mechanism of a reaction. When I will ask you of any mechanism, I will say, give a proposed mechanism. That's all. So as long as it's logical, just like any one of these, you are golden. Okay? Right. So for carbon, the most common intermediate would be carbocation, carbon free radical, carbon ion, or carbene. This very unusual. Quite common, very common, super common. Right? Carbocation, almost all reactions that we have seen so far, we had made carbocation as intermediate of the reaction. right? This slide is just to brush up your memory that some carbocations are more stable than other carbocations. So when you have chance to make a carbocation, try to make a stable carbocation, right? So which one is most stable? Tertiary carbocation. The one which is most substituted. And the one which is least substituted will be least stable, right? Now a few more equations and then we are done with this chapter. Let's talk about the thermodynamics elements of a reaction. So for that, we need to know about free energy change, because that's what determines if a reaction will be endothermic, exothermic, spontaneous, or non-spontaneous, right? So the change in free energy is equal to energy of products minus energy of reactants. All reactions are some sort of work, that something is getting converted into something else. So a reaction with negative free energy will be spontaneous and will be exothermic, meaning that they will release energy when they occur. While the reaction where delta G will be positive, those will be non-spontaneous or endothermic reaction, meaning that they require energy to proceed with them. So here's the equation by which we can calculate the free energy of a reaction. The free energy equals to gas constant times temperature, natural log of equilibrium constant. Most of these things are either constant or experimental values. So the free energy is also calculated experimentally, nothing that you can do on a piece of paper except for solve a few numericals, right? So the values of gas constant and temperature and everything needs to be in these units. There are two main factors which contribute to the free energy. One is enthalpy, other is entropy. Enthalpy is something about the heat of reaction, that either heat will be required or heat will be released, while entropy is about the randomness of the structure. How many bonds are being broken, how many bonds are being formed. So this is called entropy in terms of chemical reaction. So the actual equation for absolute free energy for a reaction is this. So the change in absolute free energy equals to change in absolute enthalpy minus temperature times absolute entropy, right? Temperature is just simply temperature. Entropy is how many bonds formed or broken, and enthalpy is heat required or heat release. Yeah. Yeah, I think I have covered this. And of course, right? Now this diagram is called energy diagram of the reaction. It's also important and noteworthy to see that what does it mean by energy is required or energy will be released is the difference between the energies of reactants and products. So for exothermic reaction, you will see that the energy of product is lower than the energy of reactant. So energy lower means what? That the product is more stable. Stable things will have lesser energy, and unstable things will be having higher energy. So in exothermic reaction, reactants will be converted into products, and you can see that the energy difference is negative. While in endothermic reaction, we will need energy, as you see that the energy difference is positive because the energy of product is higher than the energy of reactant. But in both cases, you can see that there is a threshold which the reaction needs to cross to actually start the reaction, and that threshold is called activation energy, right? So you can make any intermediate there at the activation energy point or you can have transition state based on type of reaction or mechanism that you are doing. When I say transition state, so you remember the E2 mechanism in which we had the big brackets, and I told you that the bond breaking and bond making occur simultaneously. So those things are called transition state. But when we say intermediate, all the carbocation, carboanion, and all these things which are formed, those are called intermediates. Right? So you can expect some numerical questions if you want. Alright, let's forget about it. Forget that I said that you can expect the numerical questions. Let's keep it simple. Right. For kinetics, which is about the rate of reaction. So rate of reaction means that if a reaction is to happen, how slow or fast will this be? And of course, you will be as fast as your slower, member of the team. So if a reaction occurs in multiple steps, the slowest step is generally the rate determining, because the fast steps can be very fast, but as soon as the slowest step occurs, the whole reaction can only occur after that, right? So kinetics of the reaction is studied with rate law, and rate law is also luckily determined experimentally. How we can write the equations of rate law is if a reaction is where A is reacting with B and being converted into C and D, then rate law dictates that the rate of reaction will be directly proportional to the concentration of your reactants only. So the reactants are A and B, right? So the concentration of A and concentration of B. When we take out the directly proportional, we get rate constant. So this is how we can write the rate law of any given reaction. Right? I think I've covered this already. Let's take a few examples. So if this is a reaction where NO2Cl is getting converted into NO2 and Cl2, these two are the steps of this reaction. What do you think will be the rate law? So rate law will be written on the basis of the rate determining step, which is the slowest step. And the slowest step, there's only one reactant, so that's what we will write in the rate equation. That's all. So I am not in mood of giving this type of question, that's why I said forget about it. But in some cases, you can expect questions like this. Right? But yeah, in general chemistry, you would have seen a lot of questions like that, right? Right, another example is blah blah blah. This is what's happening. The question could be that what is the overall reaction? So you can solve this type of question by simple adding them, right? So the line here, 1 plus 1, 2, so 2 H2O2, and then so on and so forth, right? You see, 1 plus 1, 2 H2O2, then this bromine cancels this bromine, this bromine oxide cancels this bromine oxide, 1 plus 1, 2 water, this is the overall. So if you are given different steps, you can simply add them like you will do algebraically, and hence you will get the overall. Right? Now, the thing which was formed in the reaction and later got utilized will be the intermediate of the reaction. And the thing which reacted with your starting material but was not formed in the final product, as we see here, would be catalyst. So in this case, you can see that bromine is the one that reacted with your reagent, but it got cancelled. So bromine is your catalyst. While bromine oxide was formed in the reaction, but which got utilized later, would be your intermediate. Right? So with that, we have finished this chapter as well. Thank you so much. A few announcements which I want before we can dismiss class. Right, first of all, question. Any question? Right, so we looked at different types of reactions and mechanisms in this chapter, and then we looked at some parameters of thermodynamics and chemistry. This chapter was really short, but I'll be happy to explain anything. I think you are just eager to go back home. Right? So let me just get down to business. This is actually last physical class. Next week class will be cancelled because of the public holiday. So I can arrange an online class which you need to attend in time. I guess there is no point of that. I can simply record my lecture and then you can attend it anytime that you want. Right? So probably over the weekend I will upload my lecture. I will see some of you in tutorials this week. And that would be it. So everyone is okay with this scheme, right? So we don't need to have an online class at a different day, a different time. I'll simply record my lecture and then you can find them on DVD. I'll see you in tutorial this week.